Looking at the spectra, it was immediately obvious that there was something wrong with the system.
We proposed that this BE star is not an outer star that is unrelated to the system, but it is actually moving in orbit with this B-type star. But the star that was thought to be a normal B-type star is actually a stripped star, so of much lower mass.
One star can steal material from the other star and strip it of its outer layers and its atmosphere. And that's essentially how you go from two kind of fairly normal stars to one which has gained mass and one which has been stripped of its mass.
And I realized that this was indeed a viable hypothesis, and it was fairly, at least as likely as ours. I was starting to sweat a little. We needed interferometric data, and we all knew that there's only one facility in the world that can get it.
We all knew it had to be with the VLT or the VLTI, and we had already actually prepared a proposal when Thomas and his team contacted us, and we were really happy about that because, we don't need to ask for the same data twice on such a competitive telescope. It makes no sense.
It was quite obvious that we should work together, and that's why I proposed it. The scientific competition is not about who is getting the data. The scientific competition is on the basis of the data.
We wanted to see if there's two sources that are far apart from each other. For our purpose, MUSE was the perfect tool to use because it would tell us not only if there are two sources, but we could get the spectra as well. This would immediately tell us if they are far enough apart to resolve them and how far apart are they.
Gravity provides additional spectroscopic information to identify which star is which.
We got the MUSE data first, if I remember correctly, and then we didn't see the wide companion, and then we needed the gravity data afterwards to check to see if there were two bright stars within the gravity range, and that was the final piece of the puzzle.
I joined, I think, the latest. Abigail was using a code I wrote to analyze the gravity data and contacted me to make sure that we explore all the possible ways we can interpret the data. I think it's nice to see, actually, in this particular case, sometimes it doesn't go this way, and even though this is the right thing to do and you can advance science, people are emotionally invested and they will maybe be a little bit blinded by this emotional investment.
I think the important thing is to focus on the science, to try not to look for who's right and who's wrong, but to think of how we can advance the question that is on the table.
In my opinion, it was really a win-win situation. Either way, we find something pretty cool, right? So I think on the one hand, we confirm the existence of the nearest stellar black hole to Earth, which is very cool. Or on the other hand, we find this really exciting and difficult to capture evolutionary stage of a massive binary stellar system.
Well, I was the one observing myself, so I saw it the very minute it came in. Looking at the data as it was fresh out of the instrument, I realized that there was no distant companion. That made it very likely that Julia's and Abby's hypothesis was right. Personally, I would have wanted my interpretation to be correct, and scientifically I have to admit that this interpretation is the far more interesting option. Black holes are honestly rather boring objects. In particular, if they're quiet, in quiescence, they don't do anything.
I think I would have been very fine with the original interpretation of that system, because in our community, people are looking for these quiescent black holes, which are very difficult to detect, and they don't find them anywhere.
The whole story of this project is that they were competing explanations, but they made some prediction. If the hypothesis of the black hole is this way, then this is what we should see if we observe with this particular instrument. And if there is no black hole, we will see something different. The observations were really designed in mind saying we can test which hypothesis is the most likely. And in the end, we have a very definite answer.
For the original question on the nature of the system, we have reached a satisfying conclusion. But now there's a lot more to learn, like the precise masses that are involved, what was the original star, what is the future of the stars, and how is this coming about.
The stripped star scenario is very exciting. Previously, we've often studied binary systems before they have interacted. But in that system, we can learn something possibly about the physics that occurred during the interaction and also about the outcome, which will then also help us to model the future evolution of the system.
This collaboration between our two teams has continued, and the proposal has been accepted to continue monitoring the system with gravity.
I think it is very important that the public understands the process of science, that it's not a machine where you crank the lever and the truth comes out, but that it is a method of discourse, which has an agreed upon and a tested method to tell you what likely works and what likely doesn't. We live in times where the societies look towards science for guidance, and under these circumstances I think it is really of great importance that the public understands how science works.